right, let's go ahead and get started, because we're a little late. So my name is Christoff. I am a cloud systems engineer at Cloudreach, and I figured instead of telling you all about Cloudreach, it would be useful to tell you why I'm giving this talk. So a couple months ago, around the deadline for the CFP for KubeCon, my boyfriend and I got in a huge fight. See, I said I was going to apply for KubeCon, but I realized there's no way in hell I'm going to get accepted. So I told him I'm not going to do it, and I was adamant about it. After he left the room, I went and I applied anyways. I figured if I got accepted, I could rub it in his face. And if I didn't get accepted, he didn't have to know. So I had to come up with an idea. And at midnight, the only thing that you can think about is why we're here on Earth and all the other stuff that runs in your head. So I wondered, why do people go to KubeCon? Why is there a con? And why are we here? So I stole a 15-year-old joke, if any of you guys know red versus blue, and I made it into a talk, kind of. But instead of starting at the beginning of time and space, we'll start in the 1960s. I wasn't born yet, and I don't really know what happened then, but my parents were alive. There was some drama with missiles, and Star Trek came out. But more importantly, someone asked a really important question. Someone wanted to make a computer do two things. Crazy, right? At one time. Now, at this time, batch processing was used, which was tedious and time-consuming. See, after about an hour of collecting batch jobs, the cards were read onto a magnetic tape, seen here, which was carried into a machine room, where it was then mounted on a tape drive. The operator loaded it up, ran it through the input system, output came out, and I mean, at this time, your programmers are doing something like this, kind of waiting for things to finish. So managers weren't really happy, and time wasn't being used efficiently. So someone was like, hey, why don't we make this more efficient? And talked about time sharing. Time sharing is when the CPU tries its best to divvy up its time between different processes. The time-sharing operating system assures that all tasks get access to the CPU one by one for a fixed small interval of time. That interval is known as the time quantum. And that way, computers can provide fast, interactive services to users and perhaps also be working on big things in the background. This is used a lot today. So now that we understand where we're going, let's go a little bit in the history, right? Where did this all begin? So in 1963, MIT announced Project Mac, standing for Multiple Access Computer. It was funded by a $2 million grant by DARPA. MIT looked at two providers for hardware, GE and IBM. IBM said, hey man, batch processing is super cool, so we're gonna stick with it. And so MIT went with GE. In 1967, Bell Labs had a similar needs, and IBM woke up and created the CP40. CP stood for Control Program, and we'll touch on it later, and it was never sold to customers, but evolved into the CP67, which was the first commercial mainframe to support virtualization. Then, in 1969, Ken Thompson, whose project progress with Multics was halted, decided he was going to work on his own operating system, which became Unix. And Unix is cool because it offers virtualization at the user level. And then previous to 1994, users would have to compile all their software they wanted to run, which didn't give true portability of software. Java, made by Sun Microsystems, allowed you to write an application once, and any computer with the JRE, Java Runtime Environment, provided software virtualization. In 1999, VMware released its Workstation product a year after the company being founded. Later, this product would be distributed freely. And then in 2018, virtualization is all around us. You can see it in all of our cloud providers and everywhere. There's VMs on our computers. So it's a big deal. But what is a VM? So I always thought this quote summarized it best. But in case you don't know, because I was that person who went to talks and didn't know, virtual machines are an emulation of your computer system. It takes the underlying hardware and allows you to partition it to be used in different ways. Instead of having one box with one OS, we can have one box with many OSs. It does this virtualization with the help of a hypervisor. A hypervisor, or VMM, Virtual Machine Monitor, control program, it's evolved over time, takes care of scheduling these guest operating systems and only sees them as processes. These processes are typically running in user mode, which means it has restricted access. If the process needs to run in kernel mode or have unrestricted access, it has to talk to the hypervisor. Now, I know this process stuff may sound familiar, and you're like, man, that sounds just like a container. No, but bear with me, I'll explain why. There's some quick vocabulary we should cover before I go on, just so you don't have to Google it. The CPU has a couple different processor modes, usually two, user and kernel mode. In user mode, it has restricted access of things it can execute. And when it comes across a privileged instruction, it must switch to kernel mode, which allows it to have unrestricted access to run. An example of something that runs in kernel mode is your operating system. And what is a privileged instruction? That's a good question. Something I have found important is that how the virtual machine handles these privileged instructions is very important to how we can differentiate it from containers. So a privileged instruction is something that needs to be ran in kernel mode, can be a system call or something else. And then when something needs to be executed in kernel mode, something called binary translation occurs. This basically means we have the guest code in the guest operating system. So we copy that code and translate it so it's safe to be ran in kernel mode. We add instructions so that it doesn't harm the hypervisor or any other guest operating systems, because that guest code doesn't know that there's other machines running with it. OK, so there's a bunch of different types of virtualization, and I'll just touch on a couple of them. So in full virtualization, the guest operating system thinks that it's alone. So when we execute a privileged instruction, it traps to the hypervisor and uses binary translation to process and execute the instruction. In full virtualization, all hardware is emulated. In para-virtualization, the guest operating system is modified to be able to process those privileged instructions via a special API uses to talk to the hypervisor. And in hardware-assisted virtualization, the processor has extensions to support specific privileged instructions for the guest. So let's take a step back. That's a lot of information, and how does this normally work on my computer here, right? Well, let's say we have a process that calls any kind of system call, open. That will go to the system call interface, which will then figure out exactly what that system call needs, which will then go into kernel mode, which will then use a table to figure out what that system call is and the routine that needs to be ran. Once that is complete, the output goes right back up. Pretty straightforward. Now, just like there are many types of different virtualization, there are many different types of hypervisors, right? So a type 1 hypervisor runs on a bare metal machine. The guest operating system believes it is running in kernel mode. It's actually running in user mode. When the hypervisor receives an instruction and inspects it to see if it was from the guest operating system or a user program running in the virtual machine. So if it comes from the guest operating system, it then arranges for the instruction to be carried out. If the instruction comes from a user program in the virtual machine, then it emulates what the real hardware would do when confronted with a sensitive instruction. It either ignores it or it traps to the guest operating system. For example, a guest application has a syscall that invokes the hypervisor. Hypervisor looks at it, sees it's meant for the guest OS invokes the guest trap handler, and then the hypervisor resumes the guest application. So how does this work on a type 2 hypervisor, which is things we know as VirtualBox, right? We can see here that there is double the context switches than a type 1. So a type 2 hypervisor runs off the host operating system, taking care of the guest operating system. Here, the trap is invoked at the host operating system. When the host operating system sees an event for the guest operating system, it invokes the hypervisor. The hypervisor, in return, asks for control of the guest OS. The guest delivers the services and asks to return to its app, which traps to the host operating system, goes up to the hypervisor, and then resuming the application. And then with para-virtualization, finally, basically what happens is all sensitive instructions are hypervisor calls, which makes the guest operating system act like a program, and the hypervisor acts like its own operating system. This means the hypervisor defines a set of procedures the guest system can use, effectively creating an API for the guest operating system to talk to the hypervisor. So what should you take away from the past 10 minutes I just talked? There's a bunch of different types of virtualization, and I didn't cover them all, but you should go read about them. And VMs are an emulation of your machine. And there's a lot going on in a VM, like a lot. Not only do we have context switches and hypervisors and all of this stuff, but it takes a lot to recreate all that hardware or virtualize all that hardware, right? So then on to like why we're here at KubeCon, containers. They're kind of cool. Let's do some history. And you've probably heard this like 50 times already, so we'll do it again. In 1979, the shroot system call was introduced, which segregated file access for processes. In 2000, FreeBSD jails were allowed for partitioning a computer system into several smaller systems called jails. In 2006, Google launched process containers. Process containers were renamed control groups a year later, and eventually merged into the Linux kernel. In 2008, Linux containers worked using control groups and namespaces, working on a single Linux kernel without requiring any kind of patches. And then finally, in 2013, containers boomed with Docker, let me container that for you, and more. And in 2018, containers are used everywhere. People call me about them. We have cons. It's a whole thing. So how do those things work, right? So if we wanted to compare containers to the knowledge we just learned about virtual machines, we can put it next to a type 1 hypervisor. Here, the container sits on top of the Linux OS, utilizing those kernel features to run, where a virtual machine has its own operating system in each environment. However, I don't know what that was, but cool. However, we can also see when we run Docker in Windows or Mac, it uses the hypervisor to spin up against Linux. So effectively, when I use Docker here, it's doing that, which is cool. As I've stated before, a container is a process. That means when we call open, it acts how it normally would. Okay? Same old, same old. But Docker gets a little complicated in all the cool things it does. And I always found this interesting. So breaking down Docker, it's a container engine, and it abstracts all the messy stuff like containerd, runc, and all this other stuff, so you have a beautiful interface to create what you need. Containerd sits below it. That's a daemon that's in charge of exposing gRPC endpoints and other low-level container management tasks. Below containerd sits runc, which is a lightweight binary that interacts with the actual C groups and namespaces. I always get these two things confused because everything has the word container in it. So container engine, container runtime, and actual containers. A good distinction to be made is a container engine, like Docker or Rocket, is an easy-to-use development tool. However, a container engine, or a container runtime, there we go, manages the image transfer storage to container execution, supervision, and networking. When Kubernetes came a big deal, people wanted to use different container runtimes. So Kubernetes was like, cool, we'll make you an interface, and you can build your own runtimes or do whatever. And so there are container runtime specific container runtimes interface specific container runtimes. And that's where you get those guys. Oh, and actual containers. I don't know, I needed a third thing, so there you go. So I keep talking about these kernel features, namespaces and C groups, but what do they actually do? Namespaces are in charge of the system resources, and there are 7 different kinds of namespaces. Each process is associated with a namespace can only see or use the resource associated with the namespace. However, resources are isolated depending on what kind of namespace we use. So, going over these real quick. In a mount namespace, we can mount and unmount file systems without affecting the host file system. In a PID namespace, your process becomes PID 1. All subsequent processes are children. Supposedly, killing the parent PID will eliminate all children. Sometimes that doesn't work out. In a networking namespace, you can run programs on any port without conflicting with what might be already running on your machine. The Ipc namespace is used for isolating inter-process communication, like sysv message queues. UTC namespaces are responsible for system identification. It allows the container to have its own host name dependently from the host system, independently. And finally, the UID or user namespace allows the users in the namespace to equal different users outside the namespace. And then control groups, that thing Google made. This takes care of monitoring resource usage. If you want to limit the amount of CPU a process can use, C groups will do that for you. So big takeaway, control groups is resource usage, and namespaces are system resources. Just keep it in your head. All right, so now I covered virtual machines and how it handles system calls and hypervisors and all that messy stuff. And I also covered containers and how they handle system calls and all that messy stuff. So now we can kind of see that containers are not lightweight virtual machines. And everyone always says this, and then I thought containers were lightweight virtual machines, and then I tried to give a talk about it, and then I had to give a talk about how I learned it wasn't that. So if you want to be like me, or you don't, just understand that you wouldn't call a container, or you wouldn't call a virtual machine a heavy container. So maybe don't call them lightweight virtual machines. They're their own thing. Here's a quote I think Jess Frizzell said, but I'm not really sure, but I like it. Containers are easy to use wrappers around C groups and namespaces. Just keep that in mind. And another key point is you should virtualize systems and contain applications, right? For your ease of testing, portability, and more, you're containing your application. However, your systems, your processor architectures, all that stuff, should be virtualized. And here's the key takeaways from the container section. Containers rely on C groups and namespaces. We all know that. They're not lightweight VMs, and they might not even be right for you. Like, I get it. Everyone wants to contain their stuff, and it's fun and easy to have containerized applications, kind of, not depending. But it depends on your application and your use case. Not all things should go in containers. I'm not going to tell you what, because there's so many variables, but know your stuff, kind of. And then Kubernetes. What is Kubernetes? If you don't know, I'm really worried about you. So Kubernetes is a babysitter, and I think that's the best way to describe a container orchestration or scheduler. But simply put, container orchestration tool, what's cool about it and other things like it, that takes care of your workloads. Let's look at some things I like. So there's more of these. I'm excluding Mesos, and I'm sorry. But to briefly cover these tools, I chose Swarm, Kubernetes, and Nomad. Swarm was made by Docker, and therefore it runs very closely with all the Docker stuff. It can run up to 1,000 nodes, and Docker just released Docker EE 2.0 product, which ships with Kubernetes with Swarm, in case you need to run them together, or you're switching from one to the other. Docker Swarm is great for people who just really love Docker, and I'm sure there's other reasons, but go Docker. Then there's Kubernetes, which comes with a horde of features that you can try out. There's a lot of different providers and things you can try too. I like Kubernetes because it's like plug and play. You just like keep trying things and praying. And then lastly, Nomad, which is my personal favorite. Nomad follows the Unix philosophy that it is simple and clear-cut. It just wants to schedule your workloads for you, and that's all it wants to do, and nothing else. And HashiCorp has other tools to like manage stuff for you, but it has one job. I wish I just had one job. Anyways, what I want to get at here, there are many different tools, and I think it's better not to look at a war between them, but like everyone has like their own personal style and beauty. Make it pretty, guys. So what should you remember here? You should contain your application for ease of testing, portability. I think I said that already. Well, it's happening again. Containers are not lightweight virtual machines, and I think this is a repeat slide. So I was going to give like a bunch of examples of like, this goes in a VM, and this goes in a container, and you use Kubernetes for this only or else. But then I got like a real job, and I realized not all companies are the same. So sometimes the right thing and the best thing are two different options. And it's up to you and your team and your company, probably your boss, to assess what the best thing is. So sometimes the right thing isn't always chosen, and that sucks, but you gotta realize there's like so many variables that I can't even go through. So to summarize, why are we here at KubeCon? I think I figured it out. There's a lot of information and tools to keep up with. It's constantly changing. They're adding new stuff. It's crazy. And how are we supposed to keep up with all this information? KubeCon's kind of like a brain dump of like, here's all the stuff people built. Look at it. And then you can start figuring out what logos you liked best so that you can put it into production. That's how we do it. So that's just the start. This is just kind of some information to keep in the back of your head when you're doing stuff, because I always yell about it and people are like, no one cares about it, so I gave a talk about it. Anyways, if you have questions, comments, you want to tell me that, I don't know, I did great, yeah, go there. And there's a Google form. You can fill out like questions and stuff, because I know people are weird about questions. Or you can ask them to me, and I'll be really sweaty and nervous when I answer them. Cool. We're good. Yes, I don't know. What time am I done? OK. Yeah, sure. Does anyone have any questions? You just want to talk to me in my little form?
Do you have this article somewhere on Medium or Hacker News?
Yeah, if you go to catonaComputer.com, it'll be there. I've never said that out loud. But yeah, catonaComputer.com, or go to my Twitter. It's like at the bottom of everything, right there. See it? It'll be linked.
Because I think I already read this article translated in Russian, for example, and was also pretty popular. So it's kind of a good article.
Popular with the motherland. Sweet. Anyone else want to talk to me? All right. Oh, what up? Oh my gosh, universal, I don't know, SysV stuff. I used to know this.
Timeshare, right? Yeah, Unix timeshare?
Unix timeshare.
Unix timeshare.
No, is it universal or Unix?
Something.
I think it's universal.
It calls back to the time-sharing systems that you mentioned at the beginning.
Unitimeshare.
You know more about my talk than I do.
This is the unconference section of the...
Yeah.
Can you explain cat on a computer thing?
I have a cat, and she gets...
Oh, the question is, could you please explain why the cat is on the computer?
Yes. Yeah, hang on 1 second. Look at this. Look at this stuff right now. Oh, you can't. So I have a cat. Her name's Galadriel, and we put Bird TV on my computer, and she watches it. It's the coolest. Anyways, that's why.
Is that like Istio with Canary deployments or something? Yeah.
No. Yeah.
Okay. Yeah.
My cat's actually running the show behind. I don't know anything about Kubernetes, so.
Unix timeshare.
Unix timeshare. I'll put that in my next one. Anyone else? Cool, it's hot up here, so I'm gonna go.